NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will decompose a rational expression into partial fractions. We'll work through a clear example step by step. Here is the problem statement. Decompose 1 over x squared minus x into partial fractions. Step 1. Factor the denominator and set up the partial fractions form. X squared minus x factors into x times x minus 1. So we propose a decomposition, a over x plus b over x minus 1. Step 2. Clear denominators. Multiply both sides by x times x minus 1. We get 1 equals a times x minus 1 plus b times x. Step 3. Expand and equate coefficients. Expanding the right side gives 1 equals ax minus a plus bx, which simplifies to 1 equals x times a plus b minus a. Now, equate coefficients. The x coefficient must be 0, so a plus b equals 0. The constant term must be 1, so negative a equals 1. Step 4. Solve the system. From negative a equals 1, a equals negative 1. Then a plus b equals 0 gives b equals 1. Step 5. Write the final decomposition. Substitute into our form to get 1 over x squared minus x equals negative 1 over x plus 1 over x minus 1. A common way to present it is 1 over x minus 1 over x. Finally, let's quickly verify by recombining the right side. 1 over x minus 1 over x equals x over x times x minus 1 x minus 1 over x times x minus 1, which simplifies to 1 over x times x minus 1. So our decomposition is correct. Therefore, the partial fraction decomposition of 1 over x squared minus x is 1 over x minus 1 over x. Let's display our example clearly. Our goal is to find constants a, b, and c such that the fraction splits into simpler terms. Step 1. Set up the partial fraction decomposition by expressing the rational function as a sum of 3 simple fractions with unknown numerators. We will use the standard setup rule for distinct linear factors. Before we proceed, take a moment to predict the next move. Step 2. Multiply both sides by the common denominator to clear fractions, then expand the right-hand side carefully. This is the clear denominators and expand rule. Step 3. Collect like terms on the right-hand side to form a single polynomial in x squared, x, and constants. Then match coefficients with the left-hand side. We will apply polynomial coefficient matching. Step 4. Equate the coefficients of the same powers of x to form a system of equations. We will then solve the linear system for a, b, and c. Step 5. Solving the system yields the constants a equals 3, b equals 5, and c equals 7. Now substitute these values back into our partial fraction form to conclude the problem. And here is the final answer. In this lesson, we'll decompose a rational function into partial fractions for the case of a repeated linear factor. Our example is x over parentheses x minus 2 close parentheses squared. When the denominator is a repeated linear factor, parentheses x minus 2 close parentheses squared, we use one term with x minus 2 to the first power and another with x minus 2 squared. So we write a sub 1 over x minus 2 plus a sub 2 over parentheses x minus 2 close parentheses squared. Next, multiply both sides by parentheses x minus 2 close parentheses squared to clear denominators. That gives x equals a sub 1 times parentheses x minus 2 close parentheses plus a sub 2. Distribute a sub 1 and group like terms. A sub 1 times x minus 2 is a sub 1 x minus 2 a sub 1. So the right-hand side becomes a sub 1x plus parentheses, a sub 2 minus 2 a sub 1 close parentheses. Now match coefficients with the left side. On the left, the coefficient of x is 1, and the constant term is 0. Therefore, a sub 1 equals 1, and a sub 2 minus 2 a sub 1 equals 0. Solving gives a sub 2 equals 2. Substitute the constants back into the decomposition. We get x over parentheses x minus 2 close parentheses squared equals 1 over x minus 2 plus 2 over parentheses x minus 2 close parentheses squared. In this video, we will decompose a rational function into partial fractions. Decompose into partial fractions. left parenthesis x squared minus 2x minus 3 right parenthesis divided by left parenthesis x minus 1 right parenthesis times left parenthesis x squared plus 2x plus 2 right parenthesis. The denominator already factors as a linear factor times an irreducible quadratic. For this mix, the standard setup is ax plus b over the quadratic plus c over the linear. Now, clear denominators by multiplying both sides by left parenthesis x minus 1 right parenthesis times left parenthesis x squared plus 2x plus 2 right parenthesis. Equate the numerators. Expand the right-hand side and collect like terms. First expand each product. Now compare coefficients of x squared, x, and the constant term with the left side, which is 1x squared minus 2x minus 3. This gives a system of 3 linear equations. Solve the system. From the third equation, negative b plus 2c equals negative 3, so b equals 2c plus 3. Substitute into the second. Left parenthesis 2c plus 3 right parenthesis minus a plus 2c equals negative 2, which simplifies to negative a plus 4c equals negative 5, so a equals 4c plus 5. Use the first equation. A plus c equals 1 gives 4c plus 5 plus c equals 1, so 5c equals negative 4, hence c equals negative 4 fifths. Then a equals 9 fifths and b equals 7 fifths. Finally, write the decomposition. The original fraction equals open parenthesis 9x plus 7 close parenthesis over 5 times open parenthesis x squared plus 2x plus 2 close parenthesis minus 4 over parenthesis minus 4 over 5 times open parenthesis x minus 1 close parenthesis. That is the partial fraction decomposition. Quick check. Multiplying back the denominators reproduces the numerator, confirming the constants. Great work! In this lesson, we will decompose a rational function into partial fractions. We'll go step by step, keeping everything visual and intuitive. Here is the example we will solve together. The denominator has two factors x squared plus 1, which is irreducible over the reals, and x minus 1, which is linear. The setup rule says, for an irreducible quadratic factor, use a linear numerator ax plus b. For a linear factor, use a constant numerator c. So we write 1 over the product equals ax plus b over x squared plus 1 plus c over x minus 1. Next, multiply both sides by the common denominator x squared plus 1 times x minus 1 to clear denominators. That gives 1 equals ax plus b times x minus 1 plus c times x squared plus 1. Now expand and combine like terms in the numerator. On the left, the polynomial is just the constant 1, meaning the coefficients of x squared and x are 0, and the constant term is 1. So we equate coefficients. A plus c equals 0, negative a plus b equals 0, and negative b plus c equals 1. Solve the system. From negative a plus b equals 0, we get b equals a. From a plus c equals 0, we get c equals negative a. Substitute into the last equation. Minus b plus c equals 1 becomes minus a plus negative a equals 1. So negative 2a equals 1, giving a equals negative 1/2. Then b equals negative 1/2, and c equals positive 1/2. Substitute these values into the decomposition. We get 1 over x squared plus 1 times x minus 1 equals negative 1/2 x minus 1/2 over x squared plus 1, plus 1/2 over x minus 1. We can write this cleanly as minus x plus 1 over 2 times x squared plus 1 over 2 times x minus 1. That is the final decomposition. Quick check. If you recombine the right side over the common denominator, the numerator simplifies back to 1. This confirms our result is correct. In this lesson, we will decompose a rational function into partial fractions. Here is our example. We will go step by step. Factor the denominator, set up the partial fractions, clear denominators, expand and collect like terms, equate coefficients, solve for the unknown constants, and write the final decomposition. Step 1. Factor the denominator. First, factor out x. Then factor the quadratic x squared minus 3x plus 2 into x minus 1 times x minus 2. So the denominator becomes x times x minus 1 times x minus 2. Step 2. Set up the partial fraction decomposition. Since the denominator factors into linear factors with no repeats, we write the rational function as a over x plus b over x minus 1 plus c over x minus 2. Step 3. Clear denominators by multiplying both sides by x times x minus 1 times x minus 2. That gives us this polynomial identity. Step 4. Expand the right-hand side and collect like terms. Replace each product with its expanded form, then group powers of x squared, x, and the constant term. Here is the collected result. Step 5. Equate coefficients for matching powers of x. For x squared, we get a plus b plus c equals 9. For x to the first power, we get negative 3a minus 2, b minus c equals negative 16. For the constant term, we get 2, a equals 4. Step 6. Solve the system. From 2a equals 4, a equals 2. Substitute a equals 2 into the first two equations to solve for b and c. We get b equals 3 and c equals 4. Step 7. Write the final partial fraction decomposition. Substitute a equals 2, b equals 3, and c equals 4 into our setup. In this lesson, we will take an expression that often appears after reading math from an image and decompose it using partial fractions. Our goal is to go step by step so you can see exactly how each algebra move works visually. Here is the expression we will decompose. First, we will separate it into a polynomial part plus a proper rational part using polynomial long division. Divide the numerator by the denominator. The leading term, 2x cubed, divided by x squared gives 2x. Multiply the divisor by 2x, subtract, then bring down the next term. Now the leading term is x squared. Divided by x squared equals 1. Multiply and subtract again. The remainder is 3x. So the division gives 2x plus 1, with remainder 3x. Step 2. We now factor the denominator and set up the partial fractions. The denominator x squared plus x minus 2 factors into x minus 1 times x plus 2. We write the proper fraction 3x over parenthesis x minus 1 times x plus 2 as a over x minus 1 plus b over x plus 2. Step 3. Clear denominators to equate numerators. Multiply both sides by x minus 1 times x plus 2. That gives 3x equals a times x plus 2 plus b times x minus 1. Now, match coefficients of like terms. The coefficient of x on the left is 3, so a plus b must equal 3. The constant term on the left is 0, so 2a minus b must equal 0. Solve the system. From 2a minus b equals 0, b equals 2a, substitute into a plus b equals 3, so 3a equals 3. Therefore, a equals 1 and b equals 2. Finally, substitute a equals 1 and b equals 2 back into the partial fractions. This gives 3x 2 back into the partial fractions. This gives 3x over parenthesis x minus 1 times x plus 2 equals 1 over x minus 1 plus 2 over x plus 2. Therefore, the entire original expression becomes 2x plus 1 over x minus 1 plus 2 over x plus 2. Summary. First, we used polynomial long division to separate a polynomial part from a proper rational part. Then, we factored the denominator, set up partial fractions, cleared denominators, and matched coefficients. Solving for the constants gave a equals 1 and b equals 2, and that produced our final decomposition. In this lesson, we'll decompose a rational function into partial fractions step by step. Here's our example. Step 1. Perform polynomial division to separate a polynomial part and a proper fraction. Dividing the numerator by the denominator gives a quotient of x squared plus 5, with a remainder of negative 24x plus 46. Step 2. Factor the denominator and set up the partial fraction form. The denominator factors as left parenthesis x plus 3, right parenthesis times left parenthesis x minus 2, right parenthesis. So the remainder part becomes a over x plus 3 plus b over x minus 2. Step 3. Clear denominators and equate numerators. Multiply both sides by left parenthesis x plus 3, right parenthesis, left parenthesis, x minus 2, right parenthesis. we get negative 24x plus 46 equals a times left parenthesis x minus 2 right parenthesis plus b times left parenthesis x plus 3 right parenthesis. Step 4. Compare coefficients. Coefficient of x gives a plus b equals negative 24. Constant terms give 3b minus 2, a equals 46. Step 5. Solve the system for a and b. From the two equations, we find b equals negative 2 over 5 and a equals negative 118 over 5. Step 6. Write the final decomposition. Substitute a and b back into the partial fractions and include the polynomial part from the division. Quick recap. We divided to separate a polynomial part and a proper fraction, factored the denominator, set up the a over x plus 3 plus b over x minus 2 form, compared coefficients, solved for a and b, and then combined everything to get the final decomposition. This workflow will guide you through many rational function decomposition problems. In this lesson, we will decompose a rational function into partial fractions. Our goal is to find constants so that the fraction becomes a sum of simpler fractions. Step 1. Factor the denominator. We first note the denominator x cubed minus 3x plus 2. Try simple roots using direct substitution. At x equals 1, it is 0. At x equals negative 2, it is also 0. Now we factor step by step to reveal repeated factors. The final factorization is x minus 1 squared times x plus 2. Step 2. Set up the partial fractions form using the factors. Because x minus 1 is a repeated factor of multiplicity 2, we include two terms, a 1 over x minus 1 and a 1 over x minus 1 squared. And we include one term for x plus 2. Step 3. Multiply both sides by the denominator to clear fractions. Then we will solve for the constants by substituting helpful x values. Step 4. Pick values of x to simplify terms. Plug in x equals 1. All terms with x minus 1 vanish, leaving 3a2 equals 9, so a2 equals 3. Plug in x equals negative 2. All terms with x plus 2 vanish, leaving 9 equals 9b, so b equals 1. Now pick a convenient third value, like x equals 0, to solve for a1. This yields 3 equals negative 2, a1 plus 7, so a1 equals 2. Step 5. Summarize the constants and write the final decomposition. We found a1 equals 2, a2 equals 3, and b equals 1. Therefore, the fraction equals 2 over x minus 1 plus 3 over x minus 1 squared plus 1 over x plus 2. Quick check. Expand the right side mentally or with algebra to confirm the numerator. In this video, we will decompose a rational function into partial fractions when a linear factor is repeated. Decompose the fraction 2x divided by the quantity x plus 1 squared into partial fractions. Because x plus 1 is a linear factor that repeats, we assume a decomposition of the form a over x plus 1 plus b over the quantity x plus 1 squared. Multiply both sides by the quantity x plus 1 squared to clear denominators. Now expand the right side, and then compare coefficients of like powers of x. Expand to get 2x equals ax plus a plus b. From it, a equals 2 and a plus b equals 0. It follows that b equals negative 2. Substitute a and b back into the assumed form. So the decomposition is 2 over x plus 1 minus 2 over the quantity x plus 1 squared. Recap. For repeated linear factors like x plus 1 squared, a and b back into the assumed form. So the decomposition is 2 over x plus 1 minus 2 over the quantity x plus 1 squared. In this lesson, we'll decompose a rational function into partial fractions step by step. Here's the example we will solve. First, notice the denominator has a repeated linear factor x squared and a distinct linear factor x plus 1. Because of that, the general form is a over x plus b over x squared plus c over x plus 1. Next, we clear denominators by multiplying both sides by x squared times x plus 1. That gives us a simple polynomial equation to compare coefficients. Now expand the right-hand side. A times x plus 1 becomes ax squared plus ax. B times x plus 1 becomes bx plus b. And c times x squared stays cx squared. Combine like terms next. Since these polynomials are equal for all x, their coefficients must match. The x squared coefficients give a plus c equals 2. The x coefficients give a plus b equals 2. And the constants c equals 2. And the constants give b equals 1. Solve the system quickly. From b equals 1, substitute into a plus b equals 2 to get a equals 1. Then a plus c equals 2 gives c equals 1. So a, b, and c are all 1. Substitute these values back into the partial fraction form. We get 1 over x plus 1 over x squared plus 1 over x plus 1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.